Morning. Today we continue to solve examples in section 1.6. I remember last time we have solved example 4. Example 5, find this limit. This is a rational function of h, or in h, in the variable h. If h equals 0, then the denominator is 0, and the numerator is 0. So we can simplify this. This is a polynomial in h. And when h equals 0, this value is 0. So this polynomial has a factor h. In fact, if we use binomial theorem to obtain 9 plus 6h plus h squared minus h over h, then 9 and 9 are cancelled, so we have a factor h. H approaches 0 means h is not 0. It's 6 plus h. So this function is undefined at h equals 0, but this polynomial function is defined everywhere. Because these two functions have same values everywhere except at this point. So these two functions have same limits. Because this is a polynomial, we evaluate this by a direct substitution. So this limit is 6. Well, this is a square, and here is a square root. Anyway, in order to cancel t squared, we multiply this one. This time we use the distributive law to obtain the square of this one minus the square of this one. And the denominator is okay, so 9 and 9 are cancelled. Also, t squared and t squared are cancelled. Cancelled, this means the numerator is 1 and the denominator is square root of t squared minus plus 9 plus 3. Well, this is an algebraic function. Algebraic function means we obtain this one by finitely many steps of using addition, subtraction, multiplication, division, and roots. So by limited laws, we can evaluate this one by direct substitution if the denominator is non-zero. So this value is 1 and 6. Show that this limit is 0. Show in mathematics, show means proof. Show. Well, because the absolute value function of can be expressed in terms of square root and squared. Also can be expressed by inequality. Inequality, if x is not negative, then this is x. If x is negative, then this one is minus x. The negative of x is a positive number. So if we consider the absolute value function in this way, then this function is defined piecewise. At the origin, at 0, the right side of this position is defined by y equals x. Y equals x means a straight line passes through the origin and of slope 1. Whereas if x is negative means on the left half plane. This y equals minus x. Y equals minus x, also a straight line. Passes through this point, passes through the origin. So this is the graph of the absolute value function. Y equals the absolute value of x. Okay, now we apply the law or the theorem involving two-sided limits and one-sided limits. Let's consider this one first. Okay, this means x approaches 0 and x is greater than 0. If x is greater than 0, then this value is x. This is a polynomial function, so we obtain this one by direct substitution. When x approaches x from the left, means x approaches 0, but from the left means x is less than 0. So the absolute value of x now is negative of x. This is also a polynomial in x. Minus 0 is 0. Okay. Because at the position 0, the one-sided limits have the same value, we conclude the two-sided limit at 0 is the common value, 0. This proves this statement. Example 8. prove that this limit does not exist, again, we apply the theorem concerning one-sided limits and two-sided limits. We consider one-sided limits. X approaches 0 from the right means x is greater than this one, is greater than 0. So the absolute value of x is x. Because x is not 0, they are cancelled. And 1 is a constant function. The value is 1. Okay, just like before, this time x is less than 0. And the quotient is -1. This is also a constant function. We have two one-sided limits are different. So by the theorem, we know this limit does not exist. This limit exists if and only if these two-sided limits exist and have same value. Here we understand, we realize the graph of this function at 0. This function is undefined, and when x is positive, this is a part of this constant function. When x is negative, this is also a constant. So at the origin, the limit does not exist. In the example 9, we have a function f, which is defined by this rule. Determine whether this one exists or not. Well, these three examples are quite similar because they are defined as somewhere in piecewise. I mean, one side is a rule, another side is another rule. Again, we consider one side the limit at 4. according to the definition of the function, if x is greater than 4, this is square root of 4 minus x. X minus 4. Then this function is, if x is greater than 4, then this one is defined and it goes to 0. From the left means x is less than 4. 8 minus 2x. In this, on this, or in this interval, the rule of